here we've got a subspace problem. We're told that we have a linear transformation T from some vector space V into some other vector space V. And in that codomain W, we have a subspace there called P. And what I want to do is show that this Q, I just named it Q so I have something easier to work with. That's basically all of the elements in V that map into this subspace P. So this Q set is supposed to be a subspace of V. It's called the preimage. So we're going to go through our subspace properties to do this. The first one is we're going to show that 0 is in Q. So we need to show this. And so this property of being in Q is that it's going to be in there as long as it maps into P. So we should see where it maps to. So T of 0, well, because this is a linear transformation, it does have to map to 0. So that's actually problem 7 in the homework. So T of 0 has to map to 0 in W. And I know that 0 is in P because P is a subspace. And so that means that by this definition of Q, because 0 maps into P, that means that 0 is actually going to be in Q. And that's the definition or the construction that we were given. So we've got this property. And so we're going to show the additive property of a subspace that's closed under addition. So let's say that U and V are in Q. Then we need to show that U plus V is also in Q. And so again, we need to rely on the definitions that were given. So the definition of what it means to be a subspace P and the definition of this set Q. So if U and V are in Q, then we get to use that definition of Q. So if U and V are in Q, then that means that T of U and T of V is going to be in P. And since P is a subspace, I know I can add those things together. So my goal is to show that this U plus V is in Q, and it might be worthwhile to know exactly what that means. That's basically the same thing as saying that T of U plus V is in P. So I need to get to that somehow, and it's just going to use that subspace property. So P is a subspace, so T of U plus T of V is in P. And then because T is a linear transformation, I can just mash that together into one T formula. Because these two things are equal, and so that must also be in P, because it's the same thing. And therefore, by the definition of Q, U plus V are in Q. So I've got that one, and then the C one, the scalar multiple is going to work really similarly. So if U is in Q, then CU is in Q for any real C. And again, that goal, that thing that we're trying to establish, so I'm going to suppose that U is in Q. And so my goal here, this statement here is basically going to be the same thing as showing that TCU is in P, right? That's that definition of what it means to be in Q. So if U is in Q, then again, by that definition, then T of U is in P. And because P is a subspace, that means that C times T of U, right, can multiply anything that's in P by a constant, is in P. And because T is linear, I can move the C inside. And that is exactly what I'm trying to show. Therefore, CU is in PQ, and that's by the definition of Q. And so I've got my three properties, and so that means that, yeah, the set Q, the pre-image, is a subspace of V.